Welcome back everyone. In the last lecture, we had seen what is the dynamical equation that governs a two-link robotic manipulator. Today, we will use the same dynamical equations to come up with controllers that will get the end effector to the position that we desire. So, in the last lecture, we have come up with this dynamics of the two-link robotic manipulator, where we had this inertia mass matrix, we had this Coriolis matrix, and this gravity vector, and all these matrices here were dependent upon the length of the arm, the mass of the links, as well as the angle theta 2 here, right? So, this means that this equation or the system that we get is a highly nonlinear system, because the coefficient matrices of the differential equation here are changing with the values of theta, right? You can, if you remember, these had terms like sine and cos inside these matrices, and which also makes this a highly nonlinear system. Now, in this course, we had always been dealing with linear systems, and then the question is, how do we control such a highly nonlinear system? So, you'll see that whatever ideas of PD and PID controllers that we have developed in this course will come to our rescue when we try to design controllers for these type of systems. Let's dive into the control problem that we have here. Now, the control problem that we are trying to solve in this case is that, suppose you know you want that your end effector has to move to a position xd yd. Now, we are assuming that from xd yd you have already calculated what your desired theta 2 angle will be and what your desired theta 1 angle would be. That we can do using inverse kinematics that we have discussed in the previous lecture itself. So, once I have the desired angles, then the question becomes, given a system, given a two-link manipulator of this form, which is governed by this differential equation, what control law should I use so that the joint angles reaches to the desired joint angles theta 1d and theta 2d? This is the question that we are asking, and for that what we are doing is, we are first assuming that ET is the error between the desired joint angles minus theta 1 theta 2. So, this is the error signal, which is basically a 2 cross 1 vector, which is basically the difference between the theta 1d and theta 1 and then theta 2d and theta 2. Remember, again, this is a 2 cross 1 vector now, because this is 2 cross 1. Okay, so this is your errors. Now notice that this becomes, so this means that from a PID control setup, if you remember, when we were doing PID controllers, we always used to take the reference to be a 1 cross 1 signal. Okay, and therefore the error signal here was also 1 cross 1. Now we are taking a 2 cross 1 error signal. Okay, so these are all, the reference is also 2 cross 1 vector. Okay, so now if this is the error, then we can maybe start with the most general case, where we assume that tau is equal to kp into e plus kd into e dot. This is nothing but the PD control law, right? Because if you recollect, what was the PD controller like? The PD controller was like something like this. We had a kd, then we had a differentiator here, and then we had a kp term here. The output of this was summed up, and the output from this was your u, which goes into the plant, and then from here we used to take a feedback, and then this was the PD controller, this was the error signal here, this was the reference, and the output u here is nothing but kpe plus kd e dot, right? And here in this case our plant is the two-link robotic manipulator. Okay, and the input here is tau. Okay, and that is what we are writing. So tau is equal to kpe plus kde dot. So we are saying that, let us see whether a simple PD controller that we had been doing for so long now helps us to get the desired joint angles. Okay, so if this is the control law, let's see how does it work. So what we will do is we will substitute this control law in the system dynamics, and when we substitute the control law in the system dynamics, this is what we get. And then from here, notice that since theta d is constant, theta dot is 0 and theta d double dot is also 0. So this error signal here et, which is nothing but theta d minus theta, and e dot is nothing but theta d dot minus theta dot. This theta d dot will become 0, and so we can write minus theta dot. So this is what it will be. So therefore I am writing a 0 here, you can see this. And now if I take all the terms to the left half, you will see these are the terms that we are left with: kp theta d, then minus kp theta, then minus kd dot theta d dot, then g minus g theta. This is this term and this one is this term. Okay, so from here we can rewrite this again in this form, where I am writing this as m theta. This entire term I am writing it in this form, where this part is 0. Okay, so this part is being written in this form. Again, this expression here, kd theta dot here, this expression and this expression I am taking it together, then it becomes kd plus c theta dot, right? But minus theta dot can be written as theta d dot minus theta dot, and that is what I am doing here. Okay, because theta d dot is 0, so this is that part. And then finally we have this expression and this expression coming together to be written in this way, and then final minus g theta equal to 0. Okay, so this is the expression. And why am I writing this in this form? Because these are error terms. You can see this is double derivative of the error, this is single derivative of the error, and this is the error term. So I can rewrite this expression in this way. Okay, now the question is, will I be able to make the error go to 0 now? Because my main idea is that my error should go to 0 as limit t tending to infinity. If this happens, theta will converge to theta d, right? Because the error will go to 0. However, now suppose, okay, theta actually at t tending to infinity, et is 0. Now if et is 0 at steady state or at t tending to infinity, what will I be left with? I will be left with g theta equal to 0. Notice, if I take limit t tending to infinity both sides in this equation, and I say that I have chosen kp and kd, this kp and kd are in our hands, right? We can choose it as we wish. So if I choose kp and kd in such a way that et goes to 0, then I am left with g theta equal to 0. Now let us try to see what does this expression mean. If you remember, g theta had terms like the mass of the links, the length of the links, then sine and cosine times corresponding to theta 2. So all these things were there in g theta. Okay, this was the gravity vector. Now what we are saying is that this term will always be equal to 0 for any value of theta that you choose, which is never true, right? Because this theta, maybe for a particular value of theta 1 and theta 2, you can get g theta equal to 0. But why will for all values of theta 1 and theta 2 will have 0 if your configuration changes? So for example, suppose, say for example, I want that my end effector has to go from this position to this position. So at this position, say this is x1 and y1, at this position I will have some desired theta 1d and theta 2d, and say this control law works and I get g theta equal to 0. So that means at these desired thetas I will get this to be 0. However, now if I say no, I do not want x1 y1, but I want that the arm should move to x2 y2, to this position. Now as soon as it has to move to this position, the desired theta angles have also changed. Then there is no guarantee that at those desired theta angles this will be true. So this is never going to be true. It might be true for one configuration, but it will not always be true. So that is why this is not possible. Okay, fine. Even if suppose error does not go to 0, what if error goes to a constant value? Okay, there is some steady state error. In that case, what will happen? And in that case, you can see that this term and this term will go to 0. but you will still be left with Kp into a constant equal to g theta, which is again not possible by the same logic that we have discussed just now. So that means this PD control law is not going to work for us. And what is the main issue? The main issue is this term. This is the term that is the main issue. So what we are going to do is that we are going to cancel this term out. Okay, and that is why we will modify our control law by adding a plus g theta here. Okay, can we do that practically or not? I'll talk about that, but we will add an extra term g theta here, and as soon as I add an extra term g theta, you see I place this control law here. If I keep on doing this, you see g theta and g theta cancels out. Now g theta is out of the equation, which means that at the end the expression that I will get will be this. This follows exactly the same route that we applied in the last case also. In that case g theta was there, so at the end we had minus g theta term, but now we do not have a minus g theta term because we have explicitly taken g theta here, which is cancelled out the g theta which was here. Okay, now look at this expression. In this expression, if I choose Kp and Kd wisely, then I can maybe make the error go to 0, right? And therefore this control law should work. However, there are some issues. Now what are the issues? The issue is that here we are assuming that this PD control law with gravity compensation. Why are we calling it gravity compensation? Because we have taken the g theta such a way that it compensates for this g theta and it cancels it out. Therefore we call it not this part is PD control, but then with that we have added a feed forward term which is the gravity compensation term. That is why this is PD control with gravity compensation. Now in PD control with gravity compensation, the assumption is that g theta is completely cancels out this. Okay, but you can understand that, see, this is the model of the system and you already know that model of a system is never accurate, which means that the g theta that I am finding out here will never be accurate. So the same way the g theta that I am getting here will never be able to cancel it out completely. Okay, however, you see, notice the g theta here. If the g theta is this, so in this case all these terms are known, right? These are the terms which are known, and theta 1 and theta 2 is what we can always measure, right? Because theta 1 and theta 2, suppose we can always measure. So if that is the case, I should be able to at least get to an estimate of g theta. You will see a demo where you will see that this will work even if this g theta does not cancel out the g theta completely. Okay, however, if this thetas are varying quite fast, then there will be a problem, and we will see that in a demo. But in general, if the reference or the desired angles are not changing fast, they are fixed basically. In that case, this procedure will work, this controller will work. We will see that. Okay, here is your Simulink model for this two-link robotic manipulator. We have the reference signal here. This is the here we have given the dynamics of the link, and then this is the controller. So inside the reference, let us see what is there. Inside the reference, we have two references here. In one of the, so we will switch these references. In one of the references, we have a trapezoidal reference, and in the other one, we have a sinusoidal reference. We will we'll toggle these two and show both the effects. Now inside the controller, you can see this law has been implemented. This was the control law that we are using, the PD control with gravity compensation. Here you will see this is the derivative part, this is the proportional part, or in other words this part. Okay, this is this part, and this is the g theta part. All these are added up. So from here you will get the input that will go into the manipulator. So this is the controller output. Okay, and this will go into the manipulator, and let us see how the manipulator works now. So here you can see the blue line and the yellow line here are the reference joint angles. Okay, and on the right you have the blue line and yellow line are the reference joint velocities. The dotted lines here are the actual joint angles, and the dotted lines here in this plot are the measured joint velocities. Okay, and you see that the reference is some kind of a trapezoidal here. You can see this. You see the reference some kind of a trapezoidal, and you will see that this control law actually helps the desired joint angles to reach to the reference joint angles. Okay, and this is happening because you see the reference joint angle is a constant now. You can see that, and see it is actually the measured and the reference is actually finally converging to the same point. Okay, so this works. So in this case, now what we will do is that we are going to switch the reference. So let's switch the reference here. We are switching the reference here. We are switching the reference to the sinusoidal reference now. So basically, now the reference trajectories will look like sinusoid. Let us run the model, and you can see now that you see the reference trajectories are now sinusoids. You can see that the reference trajectories are sinusoids now, and you can also see that the actual positions or the actual joint angles are not able to track the reference trajectories. Even the velocities it is not able to track. Look at the velocities. The velocities are also it is not able to track. There is a lag, right? Even if we wait for some time, let us wait for some time and see how does the simulation evolve. You see the joint angles are, even though the joint angles are somewhat nearer to the reference, the velocities are way off. You can see this. Okay, the blue line, check the blue line. The actual, the dotted, again remember the dotted ones are the actual measurement. Okay, you see the velocity, the position is way off. You see the position here is way off. Okay, so you can see that when you have this theta desired is quite is changing rapidly, then it becomes difficult, because in that case you are not able to get the g theta rapidly. So that is the reason actually this happens. Okay. And now there is another issue with this control law. The other issue with this control law is this. Think about it. Kp and Kd, suppose I fix Kp and Kd. Okay, now if I fix Kp and Kd in this equation, these two terms are still changing, right? Because these are nonlinear terms, and at different configurations of the robotic link, or different configurations in means that different values of theta 1 and theta 2, these matrices will be different, right? These matrices will keep on changing, and which means that the coefficients of this differential equation will also keep on changing, the coefficient matrices. Okay, and this means that the error signal or the solution to this, whatever you get, this solution will also keep on changing as the c theta and m theta here keeps on changing. Okay, so for different configurations of this link, the response of the system would be different. That is the reason we are writing that the gains Kp and Kd are fighting against a plant whose effective inertia and coupling changes with every configuration. With different configurations, the effective inertia and the Coriolis factor here, matrix here keeps on changing, and that is the reason so the response will also be not the same. So in case of linear systems, if you remember, once we choose the value of Kp and Kd, the error signals will generally die down to 0, but the response will always remain the same, because Kp Kd gets fixed, everything is fixed, and so the response depends upon the roots of the characteristic equation that we get for the differential from the differential equation. Here, however, because m theta and c theta are changing with different configuration, the response will also keep on varying. And then if theta d is not a constant, which we saw just now, like the case where the theta d was a sinusoidal reference, in the previous expression when theta d was constant, theta d dots and theta d double dots were all cancelling out, okay, or becoming 0, and that is why they were never showing up in the control law. However, if theta d is not a constant, then they will show up in the control law, and you can see the right hand side will always be there, which will be again a problem. Okay, and to take care of all this, you see, if somehow these m thetas and c thetas also we can cancel out, then this problem will get settled, and that is the reason we go for something called the computed torque control method. Now in the computed torque control method is a two-stage approach. So in the first stage we use a controller of the form at equal to this. Okay, now this is a simple controller, this is again a PD controller. Okay, and with this controller we generate what is known as, say, AT. Okay, AT is some signal that we are generating, and we use this signal AT in the in another controller, which where we are actually giving what tau would be. So tau will become m hat a plus c hat theta dot plus g hat, where this a is coming from this controller. Okay, and let us see mathematically what happens if I plug this a here. What will happen? So if I plug this a here, this is what you will get. Notice, so I am plugging this a here, this is what you will get. And this tau, basically I am putting the tau here, and then in place of a I am putting this. So you can see the left hand side here is tau, the right hand side here is basically this equation. Okay, so that is what I am doing. So when I use this controller, let's see how the equations evolve. So the equations that we will get, so the equation that we will get will be this. Now if here m hat g hat and m hat c hat and g hat, here m hat c hat and g hat are exactly equal to m theta, g theta and c theta and g theta, then you see these terms will cancel each other out. Okay, you see, at least some of the terms will cancel each other out. Let's see which are the terms which will cancel each other out. This term and this term cancels out, this term and this term cancels out, this term and this term also cancels out, and we are left with this. Okay, and now notice that m theta here is a inertia matrix, and this has to be invertible. Okay, because this is positive definite, so therefore if I invert this or I multiply this equation both side by m inverse, or pre-multiply this equation both side by m inverse, then I will be left with an equation of this form. You see, I will be left with theta double dot is equal to theta d double dot plus kd e dot plus kpe, and then I can take this theta dot on the right hand side, and this is what I will be left with, because theta d double dot minus theta double dot is error double dot. And in this equation, look at this error expression. In this expression there is no m, there is no c, there is no g, which means the response of this or the kp kd values, if we fix, once we fix it, the error signal will always have the same response irrespective of the configuration in which you are working. This was a problem in the previous case, right? And that is what this control law is helping us to do. The only thing is that in this control law there are two levels. Basically there are two levels. One is an outer loop controller and the other is an inner loop controller. It will be something like this. So you will have theta d, you have theta, and then you have this control loop. This is a PD controller, and then the output of this is AT. This goes into the next controller, which is another type of a controller, PD controller say, and then this is how the loop is like. So the output of this PD controller, is taken as input in this. So this is an inner loop, and that's why we are calling this as an outer loop. So there is a two loop structure here. It's a nested loop structure type controller. Okay, and you will see that this is the first time we are using this type of a structure, right? We have a two loop structure. You will see that this type of a two loop structure also comes up in quad rotor control. Now let us try to see how does this work. Again, we have the same setup. The only difference is that now the control law will be different. So we have the same reference signals again, and here is the controller, and this, in this controller there are these two setups. Okay, you have the outer loop, and then you will have an inner loop here. Okay, so you'll see that this should work. Let's see. Now look at the reference again. This is a reference, trapezoidal reference. So see, this reference is being easily followed by the link. See, they are overlapping. The dotted lines are overlapping the actual lines. You can see the dotted lines are overlapping the actual lines. So, now we will change the reference. Let us change the reference here. See, I am changing the reference here. I am making the reference to say 0. So, 0 means that the sinusoidal reference is on now. So, let us see. You see, initially it is way off, right? You can see that the actual joint angles are way off than the reference. Same goes for the uh, angular velocities also. But see, gradually they will converge. Keep an eye uh, on the measured angles and the velocities. You see, gradually they are converging. And now you can see that they have completely converged. So they are easily able to track the trajectories, the desired trajectory. And here in the previous case, if you remember, in that PD controller with gravity compensation case, there was some gap, right? I mean, there was some tracking error, and in this case there is no tracking error as such. So this is how the computed torque control method uh, actually helps you to get to a better controller. Actually, this is a better controller compared to this. However, that doesn't mean that this cannot be used. It can be used. So here is a comparison. So if you have fixed set points, if the desired joint angles are fixed, okay, in that case you can actually go ahead and use this controller. However, if you have fast trajectory tracking is required, and you know the model, means you know M, C and theta and G, then this computed torque control method should be your choice. If you do not have any idea about the parameters of the system, then these methods are not at all good, because you, in the first method you had to cancel out g theta, okay, and in the second method you not only cancelled out g theta, you are also assuming that m hat is equal to m theta and c hat is equal to c theta, which means these are also getting cancelled. So unless you know the model, you should not go for these methods. If you do not know the model, you have to go for some kind of an adaptive controller, and if you want some bounce on the error, tracking error, then you have to go for some kind of a robust controller. Now that you have seen how to control robotic arms, you should be able to extend this idea to higher degree of freedoms as well. Remember, in this case we have taken a simple robotic link manipulator where we had only 2 joints. You can go ahead and try to do the same thing for 3 joints, 4 joints and even for 6 degree of freedom robotic arm manipulators. I will leave that for you to explore. Thank you.